In this last video, we want to talk about the types of discontinuities that are possible when something is not continuous. And here's really kind of a snapshot of the majority of possibilities. The only one that's not on here is one that's so uncommon, and that's if you go back to the notes with numerical and graphical limits, we looked at the oscillating function, sine of 1 over x. That's the one where it's also discontinuous because of that oscillating behavior. But really, that's not a common instance. So let's consider now these types of discontinuities. First up here, we have our removable discontinuities. Those are typical because the limit exists. That would be a case where you have a hole in the graph here. You can see clearly the limit. So I could fix that discontinuity by just coloring in that dot, right? Defining the function to be that limit value. And the other possibility with a removable one is where the function value and the limit value are different. Okay, they look different than each other. So I could make it continuous just by changing that function value over. And those are called removable discontinuities. And again, it's illustrated by the idea that there is actually a limit. Okay. And then we have our non-removable discontinuities. The limit does not exist. Remember when we have these vertical asymptotes, even if it was approaching the same direction, we'd say like the limit went to positive infinity, the limit still wouldn't actually have a limit. We're just kind of describing why it doesn't have a limit in that case. So vertical asymptote, or if you have one of these piecewise functions where it's going off and changing, from one function value, one function over to another one, right? So they're not connected. And those are called non-removable discontinuities. Those are called non-removable discontinuities. And they're defined by the idea that the limit doesn't exist. So if we don't have a limit, either again because of a piecewise function switching, or because of a vertical asymptote, then that's called non-removable. And so we want to look at just one example here of checking to see what kind of discontinuities a particular function has. And so, bear with me for 2 minutes. So we want to classify the discontinuities of this polynomial function. And so the first thing we need to figure out is when is it not continuous? So we could do that by solving the denominator, setting the denominator equal to 0 and solving it, and finding those values. And then we could check the limit on each one. But there's actually a much better way with these rational functions, and that's what I'm going to show you. So the long way would be set the denominator equal to 0, and then check the limit as you go towards each of those to see whether you have a limit or not. If you do, then that's going to end up being a case where you had a hole in the graph, and it will be it will be a removable discontinuity, or you have that number divided by 0 situation, which is going to lead to a vertical asymptote, and we'd have a non-removable discontinuity. But there's actually a better way to approach this problem, and that is, let's factor the top and bottom. Okay, x times x plus 3 over x times x minus 5. And then notice that, hey, we can cancel out that common factor. And we can say, hey, that's equal to x plus 3 over x minus 5. And if we write that down, and I've done this when I've taught sometimes, and I've even done this in a calculus class, technically that's not correct. What I've just written is technically not an equality. It's an equality everywhere except when x is 0. Because when x is 0, that's 0 divided by 0. And I can't compute that. Whereas x plus 3 over x minus 5, I could plug a 0 in for x. No problem. So to be fully correct, we really do need to say, comma, except when x is 0. Okay. So that's just rewriting my function. And now we can see the value that canceled out here. Okay. That kind of removed itself from the problem. And so that's a removable discontinuity. That's a removable discontinuity. It's actually going to lead to a hole because you could compute that limit of the function because the function doesn't care what's happening at 0 when you're taking a limit as x goes to 0. So that is going to have a limit. The other one did not remove. It was still left over. And so that one is going to, and so that 0 that's left in the bottom will, of course, lead to a vertical asymptote and therefore be non-removable. So at this point, we have two discontinuities. X equals 0 because it was able to cancel out with a 0 factored in the top is a removable discontinuity. And the one that was still left over, once we reduce down as much as we can, that's a non-removable discontinuity. Okay, so hopefully that'll help you as you go through this work with discontinuities. Until next time.